Okay, welcome back. We're going to talk now about how climate change is affecting some migratory species here. And first, I want to start with just one of these. You may have seen this before. This is very famous, or I don't know if famous is the right word, but it's a video that's been seen a lot and is used a lot, taking a look at average global temperatures starting in 1881, going all the way up to, I think this one includes 2023, but we'll find out when we get to the end. And we're taking a look here at the change in average temperature, either above or below. And it is comparing it to a running mean. And so it's sort of like the running average for, I don't know exactly know what the parameters are, but basically it'll sort of take into account, say, I'm just going to make up some numbers here. Say like how much it's deviating from like the average global temperature of 20 years from 20 years previously. So in that case, it would be like, well, if you're looking at how the global temperature might be warmer or colder in 1990, it's going to be comparing it to, say, from 1950, the average from 1950 to 1970. And then when you take a look at 1991, it's going to compare it to the average of 1951 to 1971. And then 1992, it's going to compare it to the average of 1952 to 1972. So that's the running part of the mean. That the average global that it's showing you is kind of tracking the year two. But it's lagging behind. And so that's important to realize too, because it kind of gives you an idea of maybe like the rate at which things might be increasing, because the average temperature is increasing. So that running mean average will increase as well. And so red obviously means it's above average. Yellow, orange, red, above average. White is like it's right at the average for that geographical region. And then blue to very dark blue being the coldest, is below average. So just on this picture here, we're taking a look here just of the western coast of Africa here, the sub-Sahara Africa. And so this is red. So this for just this geographical region, 1981, this experience during 1981 was above average for that year compared to a previous average for multiple years. And then over in North America, we can see northwestern Canada, it was very cold for that year compared to previous years. And you can see across the globe, it's a hodgepodge, which is what typically happens every year. Some places are colder than average, some places are warmer than average. So what we're going to look here is pretty fast. We're going to track through time here. And we're going to see, and you're going to see this sort of like camouflage pattern, kind of morph and change quite a bit. And then we're going to see, which many of you are familiar with if you've seen this before, we're going to really visualize here global warming, that average increase of temperature. And we're really going to start to see things kick off here, sort of in the very late 20th century. So we'll you'll kind of notice things in 1970s, but things really start to take off in 1980 and 1990s. And then eventually we'll end in present day. So let's take a quick look. So things you can see, the hot spots kind of jump around, a little bit colder on average through some periods, getting warmer. We can really see things you can see that the poles starting to maybe show a little bit more on average warmth. 1980 now, a lot more yellow than on average. Blue's getting much more scarce here. Those poles are turning red and consistently red. And here's 2023. And so contrasting that with 1881, where it was sort of an even mix of white, blue, yellow, that one little spot of red here. And red here is 2 degrees Celsius above average. and the darkest blue being 2 degrees below average here, which has been extirpated. We don't even see that anymore. So it's stark contrast here, right? So, and we've known about this for a while, and in the sort of real time anecdotal signal that we get from year to year is becoming more and more apparent, as we can see here, and it's been right in line with the modeled predictions that we've had for decades now, is tracking things fairly well. And so this is not unexpected, what we see here, but no less disheartening. So let's take a look here and zoom in, a very specific case of this global phenomenon of global climate change, of global warming, how it's affected migratory birds. And we're going to talk about a very specific one here. We're going to talk about the barnacle goose, which has very specific areas in which it nests. And so we can see here, excuse me, at areas nesting at various coastal regions, both in Europe and over in North America, or actually in the far upper left here we have Greenland, I believe, and but they nest near the Arctic Circle, and there's also some nesting sites down here in southern Scandinavia as well, and wintering grounds here in the northern British Isles and northern coast of Central Europe, right there, just on the coast. So this is a coastal species. And so migration in birds has evolved so that the peak food availability and quality coincides with peak nestling production. And so we've talked about this in class, where the timing of spring migration and reproduction coincides with in high latitudes, the very punctuated but very productive availability of resources. And so let's go through this step by step. In 1, during our normal spring, birds migrate to their breeding grounds. You can see here in the graphic here, we're going from left to right across time. 2, relatively good condition. So they get to their breeding grounds in relatively good condition, ready to breed. Because in this species here, they've been doing they migrate via stopover migration. So they pretty easy going. They've been fueling up as they go, so they're in good condition, ready to go when they get to their breeding grounds. So they make nests, they breed, they lay eggs, they incubate. And this phase is initiated before the anticipated peak production of food. And the reason why it precedes it is because you want your nestlings to be hatched when food is peaking. So you got to get started before that peak, right? Because it takes time for the nestlings to incubate in their eggs and to hatch, right? And so in a normal year, everything's going good. We have our nestlings right here at the peak food quality, so they have the best nutrition, and they don't have to. There's no shortage of calories for your young. However, things have changed. Right? So what kind of things have changed? Well, with increased global warming, we're seeing earlier springs. And so in response, the barnacle geese, in response to an earlier spring, an advancing spring, their spring migration also advances. And so, excuse me, how do they do this? They migrate faster. And so, before we talked about the circadian rhythm, and that this is relatively endogenous and is entrained by daylight. And so these birds are sort of fettered or beholden to this ingrained endogenous physiological life history transition that isn't touched by climate change, right? Because it's ruled by day length, and climate change has nothing to do with day length. It has everything to do with temperature increasing and all the downstream effects of increasing average global temperature. And so when they get into their physiological migratory state of their testes growing, for that's the males, obviously the ovaries too for females. So I'll just say gonads, the gonad growth in the spring, and then this urge to migrate, this Zugunrui. By the time this happens, it's like, oh no, spring is like well on its way. And so the birds migrate faster because there's this, I don't know if I'm not saying that they have the subjective sort of thought that like, oh no, we're late, but they're essentially late. And what we see is that these birds in some way somehow detect this, and they try to migrate faster. And so they forego stopovers less. They either spend less time there, or they simply forego some of the stopovers, or have less stopovers as they go. And so they get to the breeding grounds in poor body condition, and they need to refuel. And so they can't advance their lane because they've just rushed so hard to get here because, by all accounts, they're late because spring has been advancing. And most of their food quality is not going by day length, but by going by things like precipitation and temperature, things like plants and invertebrates, insects. For the barnacle geese here, it's grass mostly. And so they just don't have the physiological capacity to migrate fast and, put down a whole bunch of eggs because that's very expensive to produce physiologically. And so they can't advance their lane. They do it a little bit because they migrated so fast, but not nearly enough of what they need to catch up to this early spring. And so what happens is that even though they've arrived earlier, and they're actually nesting earlier than they normally would, but it's not early enough. It's not as early as that peak food quality. And so what happens is they run into this peak before you get the peak nestling production. So they become out of sync. So the nestling miss peak food abundance and quality, most of them. And the survival of nestlings decrease because there just isn't as many calories for them during this period. And so what we call this is phenological mismatch. Phenology, this is the study of periodic events in an organism's life cycle that coincide with seasonal and climate variation. Phenological mismatch is the phenomena when these interacting species change the timing of regularly repeated phases in their life cycle at different rates. And so, so interacting species, what are the interacting species here? The barnacle goose and the food quality, or not the food quality, but the food, the grass, the vegetation here. So the goose and the vegetation here, they change their timing and of their regular repeating or their circannual phases, in this case, circannual phases of the vegetation growth production and growth, and the circannual phase of the goose migrating and reproducing. And so they changed the timing. Both the vegetation regrowth is advancing, becoming more early because of raises in increasing temperature, and the goose is changing its migration as well, but not nearly as much because it's locked into this light cycle. And so they become mismatched. They don't coincide anymore. And so this is the same story for migrants that rely on insects as well to feed their young. This is namely passerines. Even passerines are almost exclusively frugivores or nectivores, feeding on fruit and nectar, respectively, are feeding a substantial amount of insects or other invertebrate arthropods, like spiders or centipedes or annelids, worms. And so day-length Q, which is the dashed line that you see here in the upper left, we're looking at the one in which everything's in sync and everything is matched up. The day length triggers the onset of migration and egg laying. And this isn't even necessarily in the case of migratory birds, too. We get mismatch in non-migratory birds as well, but this is an example of migratory species. And so the day length Q triggers the onset of egg laying and migration for our bird, which it evolved to coincide with the match and production of as pictured here, caterpillars, which is a great food source for many passerines. They're feeding their nestlings primarily caterpillars for many species. But we can see down here in the mismatch, the caterpillar production advances, but egg laying doesn't, or it can't as much because it's restricted by day length, and climate change isn't doing anything to day length, but it's doing a whole lot to temperature and precipitation, which is what dictates when insects are going to reproduce. Spring migration coincides with leaf out of dioecious trees and caterpillar emergence. Caterpillars and birds use different cues for these behaviors. Temperature for the caterpillars and leaf out, and day length for our poor birds. Birds may face serious food shortages during breeding, and lepidopteran populations. Lepidopterans are butterflies and moths. These are the insects that produce caterpillars. Their populations may increase dramatically if they don't coincide with the predators that help keep their populations in check. And so let's take a look at some data here. Some real, not just like a picture of the conceptual model of mismatch, but let's just take a look at the data and see if it's actually occurring in a passerine bird. And so this is a study from 2006, right, almost 20 years ago now. And again, this has been repeated many, many times, and this mismatch is becoming more and more apparent for many species and for more species. And so what we're taking a look here is the peak date of caterpillar abundance. And so peak date is both graphs y-axis. And so taking a look at the top graph here, the x-axis is time, so 20 years from 1985 to 2005. We can see that the peak date is advancing. And so the April day, I should clarify this. April day, that just means the 1st of April is day 0. And so we're up to, taking a look at 1985, about day 60. And so if April is day 0, that means April, May at 60, we're talking about end of May-ish, is about 60. So into May for the peak. And then all the way here in 2005, we're here at 45. And so it's advanced about 2 weeks. So now we're looking at like the beginning-ish of May. We're looking at 45 days past April 1st, which is day 0. So mid-May. So it's advanced about 2 weeks over these 20 periods. Taking a look here at the bottom graph, mean temp and peak date. And so this doesn't coincide with year at all necessarily, though temp does does correlate with year. But we see a much tighter correlation with advancing date and temperature. So when things are hotter, from March 8th to May 17th, we see a greater advancement of the peak caterpillar date. The peak day for caterpillar abundance is at the highest temperature just 40 days after April 1st, and at the coolest temperatures 65 days after April 1st. So you can really see in this bottom graph for sure that, yeah, it's really looks like temperature is driving peak here. Let's take a look here at nestling. Number of fledgling chicks in the top growth, in the top graph here. And we're taking a look at the synchrony with food peak. And so what we see here is on the x-axis, if you're negative, that means that they were too early. And if you're positive, that means that the nestlings were too late and they missed the peak. And so we can see here for the number of fledglings, the number of fledged chicks, and this would be like per pair. So we're getting all the way up to about 12 or 13 nestlings, which is pretty good. And it would take multiple nests, and many species do produce multiple nests in one breeding season. We can see here there's a slight sort of decrease as you get further away from that perfect that perfect match, which is 0, as you get out to negative 20 and 20. We can see here it's impossible to get to even 10 chicks, let alone more. So we see this sort of shape here. It's subtle, but we got a bit of a wider base and a narrower, more narrow peak at the top. So as things become more mismatched, you have fewer chicks. And then also taking a look at the synchrony with food peak and the mean chick weight, we can see a slightly more dramatic effect here, in which if you want your heaviest nestlings, if you want your nestlings to be 20, and you can actually sort of, even hold something up to the screen right now and do a piece of paper across your screen. If you want your nestlings to be at least 20 grams, you're looking at like, well, you better make sure that you are coinciding these nestlings between less than 10 days on either side of the peak. Because if you're 15 days past, you're going to have a hard time getting these nestlings above 18 grams. And the further out you go, the harder it is to raise nestlings that are of healthy weight. So let's take a look here at 2 more graphs. This is data from 1984 to 2004, 20 years. And what we're taking a look here are at insectivore birds. 3 different kinds: residents, short, distant migrants, which tend to be facultative migrants. So those are the species that are flexible and can sort of pay attention to the climate conditions on the ground, so they can sort of advance or delay their migration and their breeding depending on the weather. and long distant migrants, which tend to be obligate, so they're sort of like really far away. They don't know what the breeding conditions are like in the breeding grounds. They just, time comes, they just go, and they tend to be more hardwired. In two different habitats, the dark boxes are forest habitats. The light boxes are wetlands or marsh habitats. And forest, and the point here is that forest habitats we tend to see, in response to temperature changes in temperature, a greater shift in peak abundance of insectivores, of leaf out and not insectivores, but insects, and other yummy arthropods that the birds like to eat and feed their nestlings, like spiders. And wetlands or marshes are less seasonal, and they're less. They experience less perturbations in temperatures because of the presence of water, acting as a kind of a temperature buffer, and so they see less of a peak shift in insect production as temperature changes. And so, who are the hardest hit here? So we're looking at the population ratio. This basically tells us how have their populations changed over 20 years. 1 means the population hasn't changed. It hasn't gotten bigger or it hasn't gotten smaller. And if it's below 1, the population is decreasing. If it's above 1, it's increasing. And so what we see here is really it's the long-distant migrants, the forest birds. Their populations are decreasing. And so it's a box plot here, so that means it's showing you a range. That black line means it's the median. And so within each box plot, there are multiple data points because there are multiple populations that they're looking at, and namely different species. And so we can see the long-distant forest birds as a group. They're all, it looks like perhaps every single one of them are decreasing. If we also had, this would be data from other studies, if we included grassland birds here, so we had forest, wetland, and grassland birds, the grassland birds boxes would be way below the this low forest bird box. It would be all the way down here at 0.1. Where they're experiencing 90+% decreases in their population across time here, and it's becoming it's and this is just up until 2004. It's become much more dramatic in the last 20 years as well, especially for grassland birds like our bobolinks. This is one of the reasons why it's so. You might see that I get so excited about the bobolinks because, as a whole, they're a species in rapid decline. In the graph on the right here, we see, again, each dot here is a species. And we can see another trend in what makes a species more vulnerable. So what we have on the x-axis is mean arrival date. So days since January 1st. And so 80, what would this be here? So you got January and February, March, so 80 would be like approximately like endish, mid to end March. And so birds that show up during this time, or this one species here on 80, and then all the way to 130. And so what are we looking at there? So let's see, January, February, March, April, mid-April-ish. So birds that are coming to the breeding grounds, May. I gotta add another one there. So all the way from March to April to May. So a lot of variation here when those are arriving. How does arrival date correlate with their population health? Well, we can see that the migrants that arrive early, their populations aren't being hurt as much because they're coming early. Even though the peak of insect production is advancing and becoming earlier and earlier, the earlier birds are already there and ready to go. But those that are coming in April and May, like, man, their migratory strategy is already way too close to peak production. So if that advances a little bit, they're out of luck. They're screwed. there's nothing that they can do to compensate. They're just simply too late. They don't have enough of a buffer time. They can't keep up. They can't get into migratory. They can't get in condition for breeding if they are trying to rush their migration, like we saw in the barnacle geese. And so, lots of different studies here across different taxa of birds showing similar things, that phenological mismatch is a problem, and as a result, we're probably seeing declines in populations that are driven, at least in part, to a substantial degree, by this phenological mismatch. Right? Because there could be other reasons why these populations are declining, but the fact that they're declining in the ways that we would predict these species to be climbing if phenological mismatch was a problem, we're seeing it. If phenological mismatch is a problem, we should expect to see that those late arriving species would have the biggest problem. We see this on the graph on the right. We would expect that the long distant migrants would have the hardest problem with this, and we see their populations declining. We would expect the forest birds compared to the wetland birds to have a harder time with this, and that's what we see when we measure the data. So all arrows are pointing towards this climate change driven phenological mismatch being a major driver for rapid population declines. Okay, we'll end it there. There's another 30-minute lecture here, a little bit introducing you to phenological mismatch and climate change and avian species.